Hi everyone, I am Dr. Kushal Roy. Today's topic of the presentation is derivative of complex functions and analyticity. So these are the outlines. Introduction, derivative of a complex function, analytic complex function, Cauchy-Riemann equations, conclusion. Today's topic is complex differentiation and analytic function, which is an important area of mathematics, especially of complex analysis, as well as in engineering. We first determine analyticity and then discuss several important properties of analytic function. There is no concept of analytic function in R, and through the introduction of analyticity in C, mathematicians added several new properties to complex functions. Complex analysis is included in BTech syllabus of all 10 streams of Dr. Bishara Engineering College, Durgapur in semester 2. Course name is Mathematics 2, course code is M302. The complex analysis is in module 4 and module 5. So let us first define derivative of a complex function. So the derivative of a complex function is defined as, let D be a domain in C and f from B to C be a function, then f is said to be derivable at a point A if limit z tending to a fz minus fa by z minus a exists in C. We denote the derivative of f at the point A by f dash. In other words, we say that f is derivable at a and the value of the derivative is f dash a if for every epsilon greater than 0 there is delta greater than 0 such that mod fz minus fa by z minus a minus f dash a is less than epsilon whenever z belongs to the domain set D with mod z minus a less than delta. So let us consider an example. It is a simplest complex function f z equal to e to the power z. Then f is clearly derivable at z equal to 0 and derivative of f at 0 is 1. Now analytic complex function. A function f from D to C defined on a domain B is said to be analytic at some point B if f is derivable at B and there is a neighborhood n in B of B such that f is derivable at each and every point of n. A function f from C to C is said to be entire if it is analytic at each and every point of C. An analytic function is also called holomorphic function. So, an example of entire function is fz equal to sine z. Here, z is the complex variable, not a real variable. This fz equal to sine z is a complex function, which is an entire function. Now, Cauchy-Riemann equation. So a function f defined on a domain D, okay, is expressed in the form f equal to u plus iv, where u is a two-variable function of x and y, and similarly v is a two-variable function of x and y. This u function, this is a real valued function. V is also a real valued function. Here x and y are the real and complex part of z, that is z equal to x plus iy. So these u and v are two variable functions, that is multivariable functions. Then f is said to satisfy Cauchy-Riemann equations at some point h, where h is h naught plus I h1 belongs to d if the partial derivative of u with respect to x, that means del u del x at h naught comma h1 is equal to partial derivative of v with respect to y del v del y at h naught comma h1. Similarly, the partial derivative of u with respect to y at h naught h1 equal to minus of partial derivative of v with respect to x at h naught h1. So let us consider an example fz equal to z square. Okay. So this is a polynomial function. In that case, f of x plus iy is x plus iy whole square. That means it is x square minus y square plus I into 2xy. So this real part of f, that means uxy, it is nothing but x square minus y square. And similarly, imaginary f, that means imaginary part of the function f, it is vxy, it is 2xy. That means partial derivative of u with respect to x, it is 2x. Partial derivative of y, with respect to y, it is minus 2y. Similarly, partial derivative of v with respect to x, it is 2y, and partial derivative of v with respect to y, it is 2x. For any x plus iy belongs to C. Therefore, this function satisfies Cauchy-Riemann equations everywhere in C. Okay, because ux equal to vy and uy equal to minus vx here. So, and z equal to x plus iy, which is an arbitrary point. That means it satisfies Cauchy-Riemann equations everywhere in C. So, another forms of Cauchy-Riemann equations. So, let us consider a domain D and a function f which is defined as u plus iv, where z is in polar form. That means z equal to r into e to the power I theta type. So r is the modulus of z and theta is the argument. In that case, at some point if actually at some point h is h naught plus I h1, and its polar form is r naught e to the power I theta naught, is said to satisfy Cauchy-Riemann equations if del f del z bar at h equal to 0. It is the complex form of the Cauchy-Riemann equation, and u r at r naught theta. U r means the partial derivative of u with respect to r. It is 1 by r into partial derivative of v with respect to theta at r naught theta naught. And similarly, the partial derivative of u with respect to theta at r naught theta naught is equal to minus r into partial derivative of v with respect to r at r naught theta naught. This is the polar form. Okay. Now, next theorem: a necessary condition for a complex function f from D to C to be said to be derivable at some point A is that a necessary condition for a complex function f to be derivable at some point A is that f satisfies Cauchy-Riemann equations at the point A. A necessary condition for a complex function f to be derivable at some point A belongs to D is that f satisfies Cauchy-Riemann equations at the point A. That means if a function is derivable, it necessarily satisfies Cauchy-Riemann equations there. Okay. Now let us consider an example of complex function which is not derivable but satisfies Cauchy-Riemann equations. So uh, let fz equal to root over mod xy, where z equal to x plus iy. So this is a complex function, and this complex function f is not derivable at z equal to 0, since if you are considering limit z tending to 0 fz minus f0 by z 0, in that case this will be limit z tending to 0 root over mod xy divided by x plus iy. This limit gives different values whenever we tend z to 0 along different paths y equal to mx, and m is where m is arbitrary. Okay. Also here, real part of f, it is root over mod xy, and imaginary part of f, it is 0. So therefore, ux00, it will be ux00 means this is the partial derivative of u with respect to x at 0, 0. That means it is limit t tending to 0, ut comma 0 minus u0 by t. If you calculate it, you can see that since in the first part ut comma 0, the y coordinate is 0, that means the value of ut comma 0, it is 0, and u0 is definitely 0, and therefore the partial derivative is 0. In a similar way, vy00 is 0, uy00 is also 0, and similarly vx00 is 0. So therefore, f satisfies Cauchy-Riemann equation at z equal to 0, but we can see that its derivative doesn't exist at 0, 0, 0. Okay. So therefore, this is an example of complex function which is not derivable but satisfies Cauchy-Riemann equation. Now, example of a derivable complex function which is not analytic. So actually, uh, if an analytic function is a function which is more than a derivable function. That means actually, if a function is derivable at each and every point of a neighborhood, in that case, it is called analytic. but it can be derivable at some isolated points. Okay, so that means you can have some function which is derivable at isolated points, but not derivable in a neighborhood. Okay, so in that case, you will get a derivable complex function which is not analytic. For example, fz equal to mod z square. Okay, so fz equal to mod z square, in that case, f is derivable at z equal to 0 since limit z tending to fz minus f0 by z minus 0. It is just 0. And here you can see that real part of f, it is x square plus y square, but imaginary part of f is 0. Thus, uxy, it is 2x, uyxy, it is 2y, but vxxy is 0 and vyxy is 0 for any x plus iy. Thus, it doesn't satisfy Cauchy-Riemann equations for any z not equal to 0. It is very much clear that for z not equal to 0, either x not equal to 0 or y not equal to 0, in that case, either ux not equal to vy or uy not equal to minus vx. Therefore, f doesn't satisfy Cauchy-Riemann equations for any z not equal to 0. And therefore, f is not analytic at z equal to 0. But here it is clear that f is derivable at z equal to 0. Now, a sufficient condition for a complex function to be differentiable. Okay, so uh, a differentiable function is necessarily satisfying Cauchy-Riemann equations. So we are giving a sufficient condition for complex function to be differentiable. So let D be a domain of C and f from B to C be a function such that fz equal to u plus iv. Okay. So u and v are functions of x and y where z equal to x plus iy. Then if is derivable at some point h, which is h naught plus ih1 belongs to the domain set D, if the following two conditions are satisfied, ux, uy, vx, vy all exist in a neighborhood of h in D. That means in some open set, in open subset of D containing H, and are continuous at H. And also it satisfies Cauchy-Riemann equations at H. If both of these conditions are satisfied, in that case, F is derivable at H. So let us consider fz equal to root over mod xy. We know that f is not derivable at z equal to 0, but it's satisfied Cauchy-Riemann equations at z equal to 0. It is to be noted that in any neighborhood of z equal to 0, none of ux and uy exist along x-axis and y-axis other than 0, 0. Okay, since they doesn't exist along x and y axis in actually any neighborhood which is containing z equal to 0, that means any open subset of C which is containing z equal to 0, it is an open ball and therefore it contains some part of x axis and y axis, but ux uy doesn't exist along x axis and y axis. Therefore, uh, it is very much clear that it cannot be derivable. Okay. So this is the conclusion. The concept of analyticity is advanced than the concept of differentiation. An analytic function has several vital properties. An analytic function is infinitely many times differentiable. That means that if a function is analytic, it is infinitely many times differentiable. There is no non-constant interfunction which is bounded. Okay. So actually, if we are considering an entire function, which that means a function which is differentiable at each and every point in C, and it is non-constant, in that case, it cannot be bounded. The zeros of an analytic function are isolated, okay, and the zero set of a non-constant analytic function cannot contain a limit point. So this is a famous theorem. Zeros means here the root. The roots of an analytic function are isolated. Isolated means actually, uh, uh, actually, mm, uh, it is said to be two zeros. That means two roots are said to be isolated if you can separate these 2 points with two neighborhoods of C. Okay. So actually, these are some higher mathematics concepts. So zeros of an analytic function are isolated, and the zero set of a non-constant analytic function cannot contain a limit point. Apart from this, there are so many properties of analytic functions. So we do not actually we don't want to actually discuss all such higher mathematics concepts. So thank you everyone.